Coincidences feel magical, don't they? You run into an old friend halfway around the world, or pick up a book and find your own name in the story. But what if those goosebump moments are not mysterious at all, but the result of cold, hard mathematics? Here's a jarring fact. Sit in a room with just 23 strangers, and there's roughly a 50-50 chance that two of you share the same birthday. 4 digits on a restroom keypad matching your secret PIN? That's a 1 in 10,000 shot, yet such matches happen all the time. Maybe the universe isn't sending messages. Maybe we're simply living inside a vast combinatorial machine. Let's start with that birthday paradox. Intuition insists that matching birthdays among 23 people should be rare. After all, there are 365 days in a year. How could so small a group yield a match? The mathematics tells a different story. Imagine shaking hands with everyone in a room. There aren't 23 chances to get a match. There are 253 pairs of handshakes, each with a tiny chance of sharing a birth date. Multiply small probabilities across many pairings, and suddenly the odds snowball to 50%. This is the same principle that makes seemingly impossible runs of identical dice rolls inevitable. Statisticians call it the law of large numbers. Roll a die 1,000 times, and it's almost certain that you'll see a streak of 6 identical outcomes. Any particular sequence is highly unlikely, yet some sequence must occur. David J. Hand, a statistician, coined a set of rules he calls the Improbability Principle, a framework for understanding why extremely improbable events occur regularly. One rule is the law of inevitability. If you give enough opportunities, something has to happen. Another is the law of large numbers. With many trials, rare events will occur. In a big city, there are so many people that almost every day someone is diagnosed with an extremely rare disease. Combine this with the law of selection, our tendency to notice the sensational and ignore the mundane, and it becomes clear why coincidences feel special. We remember the one plane crash reported on the news and forget the thousands of flights that land safely. Another principle is the law of leverage. Small adjustments can dramatically alter probabilities. Buy 1 lottery ticket and your chance of winning is minuscule. Buy 1,000 and it's still tiny but much larger. Hand's final rule, the law of almost enough, notes that we often lump similar events together. Multiple forms of lottery wins are regarded as one type of event, making them seem more common. Taken together, these principles show that unlikely events aren't miracles, but an inevitable outcome of enormous numbers of possibilities playing out over time. Consider Roy Sullivan, a U.S. park ranger who was struck by lightning 7 separate times between 1942 and 1977 and survived every strike. On average, the odds of a person being struck by lightning in a given year are less than 1 in a million. Almost 90% of victims survive, and the record number of strikes on a single person is 7. Statistically, Sullivan's experience sounds astronomical, but when you factor in millions of thunderstorms, billions of lightning flashes each year, and people like park rangers who spend countless hours outdoors, someone eventually ends up as the human lightning conductor. Our minds see a cosmic joke. Mathematics sees a normal distribution playing out its tale. Or think about the improbable story of 2 identical lottery tickets. Suppose there is a 1 in 10,000 chance of a 4-digit combination appearing. You and a stranger both choose 1, 2, 3, 4. If millions of tickets are purchased, that 1 in 10,000 shot becomes inevitable. Statisticians like to remind us that the chance of any specific sequence of 6 lottery numbers is about 1 in 14 million, yet someone wins nearly every drawing. This isn't because of luck or destiny. It's because millions of players collectively cover a significant portion of the number space. Humans are storytelling animals. We crave patterns and narratives. There's even a name for our tendency to find meaning in randomness: apophenia. It was first described in 1958 by psychiatrist Klaus Conrad and refers to the propensity to detect connections between unrelated events. You spot a butterfly on a watch and think it's a sign from your departed spouse. You see 3 green traffic lights in a row and feel primed for good luck. Evolution may have wired us this way because pattern recognition helped our ancestors survive. Better to assume rustling in the bushes is a predator and run than to dismiss a real threat. But in the modern world, apophenia often leads us astray. People pick lottery numbers based on family birthdays, even though this doesn't change their odds. A related cognitive trap is the gambler's fallacy. This bias is the belief that the outcome of a random event is influenced by previous outcomes. After a run of heads in coin tosses, we expect tails. The Decision Lab defines the gambler's fallacy as our belief that the probability of a random event in the future is altered by past events. Psychologists Amos Tversky and Daniel Kahneman showed that we suffer from insensitivity to sample size. We think small samples represent the whole. We also dislike randomness, so we invent narratives to make unpredictable events feel orderly. That's why gamblers think a string of losses means a win is due, or investors assume a streak of successful trades will continue. These biases are not limited to casinos. A judge who has approved several asylum applications in a row may subconsciously reject the next one simply to balance out their decisions. A hiring manager may alternate hires of men and women, believing fairness demands a pattern, even if the order is random. Understanding these pitfalls helps us appreciate why coincidences feel meaningful. Our brains are pattern-matching machines misapplied to random sequences. Beyond simple counting lies a more exotic explanation for coincidences: algorithmic probability. In information theory, the complexity of a pattern can influence its likelihood. The mathematician Andrei Kolmogorov showed that the complexity of a string corresponds to the length of the shortest computer program needed to generate it. Patterns that can be described by simple rules have low complexity and, counterintuitively, may be more likely to occur in random data. This concept feeds into algorithmic probability, which predicts that outcomes with simpler descriptions appear more frequently. That's why you might see repetitive sequences like 010101 or easily describable numbers like 1111 cropping up more often than messy, high-complexity patterns. In the realm of coincidences, this means that certain remarkable matches aren't as improbable as they seem because simple patterns have a mathematical edge. Another tool for understanding coincidences is the index of coincidence, a measure from cryptography that calculates the probability of two samples matching. If outcomes are not perfectly uniform, some numbers or letters are more common, then coincidences become more likely. Lower entropy, less randomness, leads to a higher chance of matches. Think of the English language. Some letters like E and T appear often. So independently drawn letters are more likely to match than if all letters were equally probable. Similarly, birthdays aren't perfectly uniform. More babies are born in certain months. So the birthday paradox's 50% threshold actually arrives with fewer than 23 people in some cases. All this talk of probability begs a deeper question. If coincidences are mathematically inevitable, does that strip them of wonder? Fisher famously observed that the one chance in a million will undoubtedly occur, with no less and no more than its appropriate frequency. When you consider the myriad opportunities for events to line up, billions of people, countless interactions, and endless combinations, it becomes clear that the unexpected is actually expected. On a cosmic scale, everything that can happen probably will happen, given enough time. Yet the human experience isn't just about numbers. We need stories to make sense of a chaotic universe. The widow who sees a butterfly land on her late husband's watch might find comfort in that coincidence. David Hand suggests that while mathematics demystifies coincidences, it doesn't diminish their emotional impact. It can even enhance our appreciation by revealing the hidden structures that give rise to them. Knowing that streaks and patterns are natural products of large numbers lets us marvel at how rich and interconnected the world is. So the next time you encounter a strange coincidence, meeting someone with your rare last name, dreaming of a song that plays on the radio the next morning, or finding your secret pin on a bathroom keypad, pause. Ask yourself, is this fate or the law of large numbers working its magic? Recognize how your brain's pattern-hungry circuitry might be weaving a narrative. Understand that the improbable is not only possible, but inevitable. In embracing the mathematics of chance, we can find a deeper, more grounded wonder, one that respects both the mystery of experience and the logic that underlies it. Coincidences aren't cosmic winks. They're the arithmetic of the universe expressed through our lives. The birthday paradox, Roy Sullivan's lightning adventures, the gambler's fallacy, and the apophenia that sees faces in clouds all illustrate how our minds grapple with randomness. The math of chance doesn't kill the romance, it simply shifts our awe from superstition to statistics. In a world where even the rarest events will occur given enough opportunities, perhaps the real marvel is not that coincidences happen, but that we are here to notice them, tell stories about them, and use them to understand the beautiful, bewildering complexity of reality.